So hello, I suppose I'm ready for this. Okay, wait, just let me. mm, Yeah, no, I think I'm ready, and it starts streaming. I thought, okay. So today, uh, I'll be exploring a article or whatever you can call it, a resource, how to scale your model. I found this resource on LinkedIn today, and I found it interesting. So आज ये read करूँगा और it got 12 sections from introduction to GPUs, and hopefully we will learn something out of it because scaling thing of LLM is like very much required in the LLM landscape and all. So मैंने भी रिसर्च अभी तक पढ़ा नहीं है, so I will be reading it live और जो भी डाउट्स रहेंगे वो भी एक्सप्लोर करेंगे. ओके, सो लेट मी जस्ट चेक कि स्ट्रीम इज लाइव और उसमें मतलब सब कुछ क्लियर है ना. सो और रुकते एक मिनट. आई एम चेकिंग ऑन माई फोन. Yep, it is working fine. So let's get start. Mm, Training LLMs. Okay. So this is from published on Feb 24, sorry, Feb 4, 2025 in affiliation with Google DeepMind and a few of the authors. You can check who are the authors. Computer scientists interested in system problems in large machine. Currently a member of technical staff at Anthropic NYC. Cool. Okay, so this is a reliable resource. And there is one more resource by HF, which is basically a playbook. Thousands of GPUs. I mean, okay, we'll be reading this one. So training LLMs often feel like alchemy, but understanding and optimizing the performance of a model is. This book is demystifying the science of scaling language models. Okay, so I will create a new scaling resource. By the way, I'll pin this link into the comment so you guys can access it or in the description. I'm gonna write things I learned from it. Okay. Maybe I'm not very well spoken, but I'm just trying. So this is my first time. So pardon me for any mistake or anything I do wrong. Okay. So okay. Now it doesn't sound really hard, and how to parallelize a model zero training and inference. So they run efficiently at massive scale. If you ever wondered how expensive should this LM be to train, okay, or how much memory do I need to serve this model myself? Watch and all together. This will be very useful. I suppose this should. Much of deep learning still boils down to kind of black magic, but optimizing the performance of a model doesn't have to. Even at a huge scale, relatively simple principles apply everywhere, from dealing with a single accelerator in terms of thousands and understanding them lets you do many useful things. Ballpark, how close parts of your model are at a theoretical optimum. Okay, so I'm thinking of taking a different approach. This article is very much long, so and I don't know that technical buzzwords and all I will understand or not at first. So I'm thinking just get into Gemini, that's it, and using Gemini to actually understand this article a little better. Article of so the article open source how to scale your model hosted by there's a talk style textbook designed to demystify the science and engineering and scaling large language models in vastly accelerated terms. Written by researchers and engineers at Google DeepMind. Its core objective is to explain strong scaling, how to increase the number of computational chips used for training or inference while achieving a proportional linear increase in performance. Score ability systems functionally how to increase the number of computational chips. And so I use Brave Search AI. So I think it's useful, very much useful. You guys should all also use it. So okay, yeah. In scaling a LM, what is the you know not proportional? What is it called? Relationship between the number of chips and what was it? Performance, computational chips and performance throughput and throughput. So throughput is the, I suppose, a clear definition of here. Let's see what it is. Scaling LLMs across multiple chips aims for strong scaling. The throughput increase. You have more shelf now. You have to submit sharding and all. The goal is linear throughput growth. What is throughput? Throughput. Okay, okay, okay. It is giving something, something, something. What is throughput? Throughput is the output efficiency, I suppose. Yeah. Throughput is the measure of how much work a system completes in a specific amount of time. The context of LLMs computing, it answers the question, how many requests can I handle per second? Wait, throughput is, yeah, what I said. The number of requests it can handle per second. How many tokens can I generate per second? Okay, so more specifically is अगर थ्रूपुट बोले तो ये है कि हम कितना टोकन जनरेट कर सकते हैं पर सेकंड इन द कॉन्टेक्स्ट ऑफ एलएम्स latency okay कितना delay होता है and all why it matters when you add more chips you're primarily trying to increase throughput you are trying to increase the number of tokens per second you want the system to handle more concurrent users larger batches without crashing while adding chips can reduce latency for massive models its primary goal is in scaling is to maximize the total number of tokens the system can churn out simultaneously. Okay, so now थोड़ा बहुत समझा. So basically it is like कि the fundamental thing कि to increase the throughput, to increase the number of tokens per second the LLM generates, uh, chips को increase करते हैं. But instead uh, it doesn't necessarily do that. What it does it manages the number of concurrent users. I suppose these are the two and the same thing. Okay. Okay, so scaling across multiple chips aims for strong scaling. The throughput increase proportionally with the number of chips. Okay, so if you increase the number of chips, the relationship between the number of chips and the throughput is proportional. But this is constrained by communication overhead and memory bandwidth. How's it? So it has attached some resource. Okay, so we are creating communication overhead. Section introduces the concept of roofline analysis, which is fundamental foundational framework used to determine what limits an algorithm performance. Okay, roofline analysis. It explains how to ballpark how close parts of an ML model are to their theoretical optimum. That outlines the three fundamental constraints that bound any distributed machine learning algorithms: compute, communication, computers floating point operation flops. Okay, flops, floating point operations, compute, okay, communication, how fast chips talk to each other. Okay, so it is like if you have distributed a model, like you have sharded the model into several GPU chips, Blackwell chips or something like that. I don't know the exact thing. So how fast they communicate to each other to serve the user, something like that. Communication, I suppose. Memory bandwidth, uh, how fast data moves between high bandwidth memory and the processor. How fast data moves between high bandwidth memory and the processor. Okay. How so the chapter one answer this question. How long should a matrix multiply a certain size take? At what point it bound by compute versus memory? Okay, so matrix multiplication कितने मतलब हाउ मच स्केल मतलब कितना बड़ा एक मैट्रिक्स होगा कि वो कंप्यूट ज्यादा लेगा इन सिंपल वर्ड्स ये बोलना चाहता है गेस ठीक है हाउ डू थिंक अबाउट टीपीयूज a deep dive into the hardware architecture of Google tensor processing unit TPUs and how they differ from standard processors of GPUs. It breaks down the physical layout of TPUs, including their systolic matrix, multiply unit, MXUs, and the vector processing unit GPUs. It details how TPUs clusters are physically wired together, the bandwidth of different parts of the system, and how very long instruction word instruction schedules keep the execution pipeline steady. Core value, okay, the sharded matrix is and how to make them. An explanation of how model studying and multi-device parallelism through the lens of most common deep learning operation matrix multiplication. All the transformer math you need to know. Okay, the exact number of parameters in a model, the total number of flops required during an forward pass versus backward pass, 5 to 7 training and inference, the core of the book. It's about chapter handles the ultimate practical question. Given a model of a specific size and a set of number of chips, how do you parallelize it to stay in a strong scaling regime? They break down four primary architecture parallelism technique used to segment model over multiple chips. Data parallelism, replicating the data, splitting the batch. Tensor parallelism, splitting individual intra-layer matrix multiplication across chips. Okay. Pipeline parallelism, splitting different layers across a sequential chain of chips. Expert parallelism, used for mixture of experts. Okay, okay. So we got the idea in chapter wise कैसे roof line analysis. So what is roof line analysis for the users? I know roof line analysis is basically fundamental analysis. You could say simple in simple words. Roof line is a performance modeling technique that plots kernels or application achieve performance against its arithmetic intensity. It's too technical, leave it. Okay. The goal is linear throughput growth. Adding more chips should decrease computation. So ideally, what should happen is you increase the number of chips. The throughput should also increase proportionally. But that is ideal scaling. But adding more chips should decrease computation time proportionally. Okay, same thing. Increase throughput or decrease computation time proportionally. Uh, Communication bound. The chip count increases the time spent moving data between devices. Okay, if communication time exceeds computation time, the system becomes communication bound and adding more chips while diminishing returns or even performance degradation. Bandwidth dependency and aggregate memory. Hardware limits. Current system using HBM3 can reach 600 user tokens per second with 128 chips for large models, but hitting 1000 tokens per second often requires smaller models. Okay, so let's start with this. You got the gist of what is this about? Okay, okay. Then with understanding and comparison promotes models. playing. Ideally, what I would do is, if I don't know about any subject, like I don't know about skilling at all. This is my first time to ever I have reading some resource about skilling and all. So what I would do is I would go to any LLM. In this case, Gemini, and I would do the same thing. Like I would ask him that how would you explain this to someone who don't know at all about this subject with first principles. So uh, the idea behind the first principle is that just the idea behind the first principle is that you understand the core of things, like why is this and what is this, why are we studying this, or why is this important at all, and where did it came from. Like the okay, to understand how to scale a massive AI model from scratch, we have to look at it first. Instead of looking at complex code or massive server racks, we need to break data from the roofline of physics. If you want to move a mountain of dirt, your speed is limited by three things: how fast your workers shovel, how many well burrows you have, and how wide the paths are between them. Computer chips, GPU, and TPUs face the exact same physical constraint while running AI models. Every calculation is bound by a roofline. Okay, AI model slows down not because of bad programming. It's a physical ceiling in one of these buckets. Scaling engineering is the science of keeping all three perfectly balanced, so no chip sits idle. Mhm. Okay, so I'm thinking of making some diagrams to understand me better. It's like a mind map. I don't know if I can do that on. Uh, yeah, I would do something in my existing doc. Okay, what is this? Okay, How could I write something over here? I don't want to generate diagram. I want text. Array, bhai, I can. Oh, fuck. Fuck it. I'm just going to write in this one. So, what's the thing? The thing is, the the fundamental, yeah, fundamental constraint for AI to scale comes down to three things. The first is compute, how fast or how many mathematical operation like adding, multiplying, and all a chip can perform physically per second. First is uh, compute, which is how many operations or flops, that is uh, floating floating point operations or flops a chip can perform uh, physically. Second is I can increase its size, right? Uh, let me. Then I memory bandwidth. A chip has a brain like a processor and a store room, high bandwidth memory or HBM. Memory bandwidth is how fast data can travel from the storage room into the processor's brain. Uh, chip has a brain, the processor, and a storage room. Memory bandwidth is how fast data travel from the storage room to the processor's brain. The brain is incredibly fast, but the wheelbarrow is slow. The brain sits idle waiting for the data. Okay. So, second is memory bandwidth. Uh, First is computation, second is memory bandwidth. Okay. Memory bandwidth. So basically, how much a processor or a oh wait, chip has a brain. Communication. When a model is too big for one chip, you use thousands of yeah, the sharding, the one I said. I can just copy it, right? The same thing. I think writing in my own words or oh, sorry. The memory bandwidth I didn't understand as well, but okay. What was this example? How many wheelbarrows you have? So basically, how much of thing you can transfer, how fast. The chip has a brain, processor, and a storage room, high bandwidth memory or HBM. Memory bandwidth is how fast data can travel from the storage room into the processor's brain. The brain is incredibly fast, but the brain varies. So, okay, so how fast it can travel? The core is that this one. No, fuck. How fast data can travel from the storage room into the basically storage room is that storage room is this compute where the data is getting stored in a chip. Okay, in a chip from a chip, how fast it can get into the chip's processor. These are three fundamental things. Okay, an AI model slows down not because of that code, but because it has physical ceiling in one of these three buckets. Scaling engineering is a science of okay, so understanding. Yeah, this is nice. Again, the science of keeping all three. Can I increase the size of it? I'll leave it. So scaling engineering is this on it. The anatomy of the hardware chip. But I okay. To understand how an AI model runs, you have to understand the physical tool executing it. The book focuses heavily on the Google CPU. From first principles perspective, standard computer chip CPUs are designed to do a little bit of everything, making them jack of all trades. TPUs, however, are factory assembly lines built for one specific purpose: matrix multiplication. For those who don't know, TPUs stand for Tensor Processing Unit, and it was designed by Google especially for this AI stuff for matrix multiplication. So that's what this Gemini is saying that CPUs were before GPUs or yeah, CPUs were before GPUs and TPUs, and GPUs came for the task mostly the gaming and all the graphics thing. But the TPUs are specially made for this AI matrix multiplication only because inside inside the AI, what's happening is like it's nothing but you need to understand. Just there are too many matrix multiplication happening. That is the process happening. You know, to answer you, the AI is doing that. I'm not very well spoken. I said that, so just forgive me. I'm just trying to do a little bit. It's, okay, so inside the TPU, data flows like a water through a grid of processing nodes called a systolic array. TPU architecture, I don't know I should do that or not because this is not, none of the concern. Okay, we'll see that. Hardware design dictates software efficiency. Okay, we don't need to know TPU overall. We know enough. Sharding, splitting the monolith. Imagine you have math problems, so math center requires a billion calculations. Single, okay, starting is just a giant grid of numbers representing the area's knowledge, data parallelism. You give random eliminations will copy you split a problem among multiple workers. So sharding is nothing but the splitting of uh, models. Basically, you have a large model like GPT of several billion parameters. You cannot just store it in a single GPU because it cannot handle the multiple concurrent requests or tasks. So what basically happen is like in industries or this frontier labs, what they do is they split the model into several GPUs, let's say, and based on the and when the request is being transferred or request is being passed to each and every GPU, which communicate to each other and solve the problem and then answer to you in simple words. I don't know if I was able to frame it properly or not, but that's what it is. Like you can read it over here. Sharding imagining a math problem so massive that it requires a million calculations. Single human brain would take years to solve it. To speed it up, you hire 100 mathematicians. But how do you divide the work? This sharding in AI, matrix is giant grid of numbers representing the AI knowledge. So you divide it using two ways: data parallelism or tensor parallelism. What is data parallelism? You give every mathematician a full copy of the AI model, but you give them different sentences, data to process. Yeah. So basically, the same AI is there are several GPUs which has the same AI. Like this has a 7 billion parameter Gemini, 7 billion, 7 billion, 7 billion. And when the request comes, the request gets equally divided to each of them. So it's a concept of data parallelism. You divide the request to each of the fully model, like the models with the full parameters. Tensor parallelism is like the model is too big to fit in one chip memory. The one which I said, like you divide the model into several GPU architecture. So you slice the giant grid of numbers into smaller blocks. Chip A gets the top half of the grid, and chip B gets the bottom half. They must work simultaneously to calculate a math problem. So what they do is like there is a math problem. So one half is calculated from this GPU side, left one, and the other half is right, and then the both merge the whatever communicate to each other and then answer to the math of a transformer. So you must know the what are weights, what are activations, and all. Training versus inference. So training is like training, and inference is like testing. Yeah, this is basic. So now I think we are good to go to read this. How I explain so okay. Much of deep learnings will boil down to kind of magic, black magic. But optimizing the performance of a model doesn't have to. Even at a huge scale, relatively simple principles apply everywhere. From dealing with a single accelerated tens of thousands and understanding them lets you do so many useful things. Ballpark how close parts of your model are to their theoretical optimum. Make informed choices about different parallelism schemes at different scales. Estimate the cost and time required. Train. We are going to assume a basic understanding of LMs and the transformer architecture, but not necessarily how to operate at scale. We should know the basic of LM training and ideally have some basic familiarity with JETs. I don't have familiarity with JETs at all. Okay, so okay. Some useful background reading with might include this blog post. Okay, on the transformer architecture and the original transformer paper. Also, so if you guys okay, what someone is watching. Mm, cool. Much of deep learning still boiled down to kind of magic. Like, By the end of, you should feel comfortable estimating the best parallelism skin for a transform model on a given hardware platform and roughly how long training and inference should take. If you don't, email us or leave a comment. We'd love to know how we could make this clear. You might also enjoy reading the section 12 on NVIDIA GPUs. Why should you care? 3 or 4 years ago, I don't think most ML researchers would have needed to understand all the content in this book. But today, even small models run so close to hardware limits that doing novel research requires you to think about efficiency at scale. 20% win on benchmarks is irrelevant if it comes at a cost of 20% to roofline efficiency. What does roofline means? Yeah, 20% win. 20% model architectures routinely fail either because they can't run efficiently at scale or because no one puts in the work to make them do so. Goal of model scaling is to be able to increase the number of chips used for training or inference. So what is strong scaling? Okay. The goal of model scaling is to be able to increase the number of chips in the training and the inference while achieving a proportional linear increase in throughput, increasing the number of output. This is known as strong scaling. Although adding additional chips parallelism usually decrease the computation time. It's comes at the cost of credit communication between chips. So what? Okay, what's so even if we increase the number of chips or the number of flops, whatever it is, it increases the number of throughput. That is right, but it comes with a cost of the communication between the chips, the processor. So what it is saying is that we become communication bound even if we increase the number of chips. Adding additional chips usually decrease the computation time. It also comes with the added cost, which is communication bound. Okay. So our goal in this book is to explain how TPU hardware works and how the transformer architecture has evolved to perform well on current hardware. We hope this will be useful both for researchers designing new architectures and for engineers. This is a nice thing to understand. So why scaling laws? Sorry, why this is high level outline. Section 1 explains roof analysis and what factors can limit our ability to scale. The three factors we already studied that communication, computation, memory. Section 2, Section 3 talk in detail about how TPUs work. Okay, both as individual chips and of critical importance as an interconnected system with interchip links or limited bandwidth and latency. We'll answer question like how long should a matrix multiplier of a certain size take? At what point is it bound by compute or by memory or communication method? How are the TPU wired together to form twin clusters? How much bandwidth does each part of the system have? How long does it take to gather, scatter, or to redistribute arrays of approximate TPUs? How do we efficiently multiply matrices distributed infinitely across differently devices? HBM, I thought, here it is. I suppose HBM is the high bandwidth memory. Okay, so we should also write this, right? Few acronyms. HBM stands for high bandwidth memory. Then flops stand for floating point. I know that, but okay, floating point operation. Okay. showing how our TP performs an element-wise product depending on the size of our array and the bandwidth of our links relations. We can find ourselves compute bound using the full hardware compute capacity or as a row ML had a colorful landscape of our architectures, connects, LSTMs, MLPs, transformers. But now we mostly just have the transformer. We strongly believe it's worth understanding every piece of the transformer. So, so guys, I know कोई देख नहीं रहा है बट अगर जिसको भी ट्रांसफॉर्मर आर्किटेक्चर चाहिए तो मैं एक वीडियो बनाने वाला हूँ thinking this is my first video only so let's say कल परसों तक मैं एक ट्रांसफॉर्मर आर्किटेक्चर के ऊपर एक डिटेल एक्सप्लेनेशन और कोड इफ पॉसिबल बनाता हूँ ठीक है because everything and anything you study about AI, I mean core AI, you need to know transformer. It is the absolute basic. You just need to know transformer. There's no, shortcut to it. Okay. Listening every piece of transformer is just every much right. Normalization occurs. How many parameters and flops? Should not a con. The stream will get recorded. That is good. Okay. These are the symbols and that yes. Section 5. Link to the section. Okay, next one. When we run algorithms on hardware, we are bounded by checkpoints. How fast a computer can do math? What is the revenue takes fucking मत आओ दूर रहो नहीं रुको रुको अरे हाँ अभी लाइव चालू जाओ आप यहाँ से ये सब बोलने लगा नहीं सब 50 seconds or 5 seconds. What is actually happening within all the substitution? Even more is actually a bunch of this क्या होता है multiplication is composed of floating point multiplication and addition. Accelerator speed determines how long this take to compute. Computation flops upon accelerator flops. No, accelerators so in context of AI, an accelerator is a piece of specialized hardware designed explicitly to handle the massive, repetitive mathematical workloads required by AI and machine. A standard computer can run AI models in theory. Things on a normal processor is incredibly inefficient. Hardware accelerators are built to speed up. There are a few incredible powerful brains that can switch between running on operating system and web browser or mouse. It's built for low latency on some tasks. So is it like a function simply to of uh, LRU is recently used LRU cache. It is actually a beautiful combination of both, but scaled up to a massive hardware level. It acts like a function performance in operation. This is a complete part of the accelerator. The chip is hardwired with a singular massive function run into its physical silicon. The memory part of it. Hardware and performance. Okay, I will continue with this. Understand what accelerators are. Accelerators are a function that optimize or increase the speed, compute speed. I mean, it could do like anything, like having a cache management, as I said, something else. So okay, so basically the time to do the math. This is T math is the time. For instance, NVIDIA H100 can perform about 9.89 E14 B float. So for those who don't know, this is I don't know what is this. Okay, maybe the number. B float is like binary float, 16, 16 point precision flops. Flops. While a TPU inform these flops. What is this? You need to understand this. You know to get this that. Oh, it is written. BF16 is short for B float 16, a 16-bit. Yeah, I know that. What is this? E 9.89 ये थोड़ा ज़्यादा लेता है और ये थोड़ा कम लेता है 9.19 to perform. Okay. Uh, I think this is a number, but this is a number written in scientific notation. Oh, my bad. Exponent. So exponent and means times 10 to the power of. So 9.89. E14 translates to 9.89 exponent of 14 into the power 14. Okay, I know that. So this much floating point operations while a TPU V6E. Okay, let's see. NVIDIA H100 or TPU V6E can perform this much flops. That means doing one exponent 12 flops on H100 will take roughly around 1 milliseconds, and the same on TPU will 1.1 milliseconds. Communication within an accelerator, tensors need to be transferred between accelerator memory, HBM, high bandwidth memory, and the compute cores. You will see the bandwidth of this link referred to as HBM memory on an accelerator. It's looking a bit technical, but I think we'll. Oh no, this section is too big. Few problems to work on. I think we where does the time go? All about roofline. Just need to do it fast. It's already 1:30. Okay. CPU takes more time than the GPU in accelerator time. So it is the communication part. This was the compute part. So the compute part, the GPU or specifically NVIDIA H100 computes this much flops in this much time, 1.01 milliseconds, and the same CPU V6E does in 1.1 milliseconds, which is more. Okay, for the communication, the H100 takes 3.35 TBs. TBs, what is TBs? Terabytes. Communication. Array, I was not asking that one. I don't know if that is the same thing. Oh, this Gemini now. I need to refresh. I suppose. Uh, need to refresh. I mean, terabyte per second. Okay. Ah, we are. The represents this is a nice breaking. Okay, right. Yeah. To take, I did. I'm doing it for myself and for you guys if you need later. Because I cannot, you know, copy. And I will take screenshot. I suppose that's a lame way to do it. Uh, get out of my way, bro. Where is the screenshot? Can't attach it. I'll leave it. Fuck. Go write the equation. The okay. About math jacks, math, copy the keyboard, math ML code. What is ML code? Oh my god. Okay. It got pasted below. I thought it was pasted. Oh, okay, okay. Delete, delete you. Yeah. E to the power. What I wrote on what I wrote. I never used it. Distribute the model across many accelerators. Tensors frequently need to be transferred between them. Okay. Okay, so I understand now what accelerator intentionally mean over here. I think it's oh, it is might work. Is it not working? Fuck. It wasn't working. That's insane. You'll see bandwidth of display capacitors is from okay, accelerators, tensors frequently need to be transferred between them. There are often a few options for this on our hardware. ICN, BCN, CAD, it's with I think my mic isn't working. It's not. charged. Peripheral component interconnect express the elevator inside the building. What it is? Peripheral component interconnect express is a standard physical interface used to connect the computer's brain, this main processor, to its internal peripherals like graphics card, solid state drives, and but also it uses physical lanes. Okay, okay. I said interchassis interconnect. ICI is a specialized ultra high speed network built custom by hardware manufacturers to link multiple AI chips together within the same server rack or adjacent rack by passing the slow GPU entirely. Example, Google calls the ICI used to link GPUs via optical circuit switches. NVIDIA's equivalent is NVLink. Yes, so there are several components through which the communication happens between the racks, different racks. Racks. Communication within a chip, communication between the chip. The communication within a chip, an accelerated tensor, message transfer between the circuit. Communication is within a chip, within chips measure this by itself. That's what the total communication within. T of communication, communication bytes per network bandwidth. Um, ICI, DCN, then PCIe, peripheral, what was it? Peripheral component interconnect express. Okay, this is standard. DCN stands for technologies. DCN is a data center network. DCN is a traditional large-scale networking infrastructure that connects thousands of independent server racks across the entire data center floor. All of it is important. So, understand. Essentially, all of these are the techniques or components used for sharing the data between the racks and within the racks. Yeah, I hope I'm clear. That was I see. Yeah, I see. I see. Interclassic interconnect. Okay, few examples. NVLink or ICI is a specialized ultra high-speed network built custom by orders to link multiple AI chips together within the same server rack or adjacent rack by placing them. Okay. So these are the custom solutions built by the companies like the NVIDIA's NVLink and all. Stands for what? Stands for interclassic interconnect. Should know these terminologies. There's more to it. There is more to it. अरे आइए राइट इंटर क्लासिक interconnect. Yeah, yeah, sure. It's not classic. Inter chessic triple S. The completion is around typically okay. Computation within a single chip can be overlapped with communication within a chip between chips. That is the maximum. Little bit what I understood in OA is the stream is now almost 2 hours long. Okay, I know no one is watching the stream right now, but I'm gonna end this stream because it's already 2 o'clock, and this is my first stream, by the way, first video. So thank you for watching. If anyone did in future, or forgive me for wasting your time if I did, and thank you.